Hi, this is Patel. In this lecture, we are going to learn few basic concepts to solve the numericals based on shear force and bending moment diagrams. We have already seen the concept of how to calculate the shear force and bending moment for different kinds of the load. Different types of the beam and load were already discussed in the previous lecture. So if you have not studied those lectures, then I would suggest that you should go back in our playlist and understand those concepts very clearly. Using those concepts, we are going to understand how to solve the numericals for different types of the loading. So first of all, we will start with our first example. The examples which contains a point load and uniformly distributed load. So as you can see on your screen, the diagram of beam loading is shown on your screen, where you will see that there is a design which is used for the UDL. This is our UDL, which is having the value of 10 kilonewton per meter. So this is basic unit of UDL. It is represented by Newton per meter or Newton per mm or kilonewton per meter. So first of all, this load is always acting in the downward direction. So let me assume that point A to point C is subjected to a uniformly distributed load. Now at point C, you will see 80 kilonewton load acting on the beam. So 80 kilonewton is a point load because it is acting at one point C only. At point D, you will see that there is a 40 kilonewton acting on the beam. Now the distance between each and every point is already given in your diagram. What you have to do is clearly instructed over here that draw the shear force and bending moment diagram for the beam loaded as shown in a figure. So in most of the examples, this type of instruction will be given to you. And you will have to draw a shear force and bending moment diagram using the basic concept that we have studied in the previous lecture. So what you have to remember for this particular example, that whenever you are drawing a shear force diagram for point load, then you will connect 2 points using the horizontal lines. Whereas in the case of uniformly distributed load or UDL, the shear force diagram will be connected using an inclined line. Now, whenever you are drawing a bending moment diagram for point load, points will be connected using the inclined line, and for UDL portion, the points will be connected using the parabolic curve. So we are going to calculate the values at first, and later on we will plot the diagram using those values in this particular example. So the method of solving this type of examples are pretty much the same. So I would suggest you to solve the similar kind of the examples from the exercises available. So we will start with the next step of the example, that is nothing but the beam reactions. In each and every example, you will have to find out the beam reaction first in order to go further. So we already know how to solve the beam reaction. First of all, you need to take a moment at any point on the beam. We are taking the moment at point A. So at point A, we are going to take the moment of UDL first. So instead of UDL, we can convert it into a point load, which is subjected to the center of the UDL. So what is which one is the center? It is located at 1 meter distance, like this. So what will be the value of this point load? It is nothing but the total UDL into total distance. Total distance is 2 meter. So 10 into 2 is our total UDL or uniformly distributed load. What is the distance from the point A is nothing but the 1 meter. This is our 1 meter distance. So what we have done, total load, that is 10 into 2 into distance, that is 1. So this is our moment due to the UDL. As you can see, UDL is always acting in the downward direction. So due to downward direction, the moment acting will be in the clockwise direction. Now we will go further at the point C. You will see a point load which is also acting in a downwards direction, which will be constituting a clockwise moment. So the direction is the same. That's why we are going to use positive sign. If it is an anti-clockwise moment, we would use a negative sign. The moment due to 80 kilonewton is force into perpendicular distance. How much distance is there between A and point 80 kilonewton? It's 2 meter. So 80 into 2, that's our moment. Now at point D, there is another force 40 kilonewton. This is also acting in a downward direction, so clockwise and positive. So 40 into 3 is our clockwise direction moment. Now this RB or the reaction at B is going in the upward direction. So due to the upward direction, it will create anti-clockwise moment. Anti-clockwise moment, that's why we have represented it on the left hand side. On the left hand side of the equal to. So RB into total distance up to A point is nothing but 5 meter. So in this particular relation, you will see there is only one unknown remaining, that is nothing but our RB. So if you make RB as a subject, put 5 in the denominator of the right hand side and calculate, then you will get the answer of the RB as a 60 kilonewton. We know that RA and RB are the reactions which carries the entire load of the beam. So RA plus RB equals to total load, and what that total load is 20 plus 80 plus 40, which we have already calculated using our basic concepts. Now if you subtract the RB from it, you will get the answer of RA, which is nothing but 80 kilonewton. 80 kilonewton is the answer of Ra. So this is how we calculate our support reactions at point A and point B. Now let me just clear it out so that you guys can understand further more explanation. We will move forward for calculation of shear force. Let me just go through it. So the shear force is calculated at each point of the beam. So first of all, we are going to look at the point A. Here in your diagram, you can see that we have also written the value of RA and RB. Both the values are already written in the diagram. Now what we are going to do, we are going to calculate the value of shear force at the point A. So at the point A, we are assuming a imaginary section like this. On the left hand side, there are no other forces acting on the beam. So only Ra value will be our reaction support shear force at point A. The value of Ra is equals to 80. That's why shear force at A is equals to 80. Moving forward, we will see at point C, we are going to take one imaginary section. On the left hand side, there are two forces acting on the beam. The first one is the Ra and the second one is the UDL that you can see over here. So first one is Ra going in the upward direction. So you will see that Ra is going in the upward direction, but UDL is always acting in the downward direction. So both the forces are in the opposite direction. So we are going to take the moment algebraic sum of the both the forces. According to our sign convention, on the left side, upward direction is taken as positive. So the upward force is 80 kilonewton and UDL is downward. That's why it is taken as negative. Also, there is one point load acting at the point C, that is 80, which is also in the downward direction. That is why we have taken 80 as negative. So by taking the algebraic sum, you will get the final answer as a minus 20 kilonewton. So this is our final answer at the point C. Now move forward toward the point D. At the point D, this much forces are already there, and we have already made an algebraic sum of these forces as a minus 20. So we are going to take that directly. So minus 20 is taken from previous point. Now, which force is getting added at the point D? It is 40 kilonewton. 40 kilonewton is going in a downward direction. So as it is in a downward direction, that is why we are going to take it as a negative. So it's minus 40. It is minus 40. So final answer comes out to be minus 60. Next is point B. At point B, you will see the algebraic sum of all the forces will go to 0, because the shear force acting in the at the point B is 60 kilonewton. So 60 kilonewton is in the negative direction. So positive 60 and negative 60 will go down to 0. So this is how we calculate our shear force. Now what we are going to do, we are going to draw a shear force diagram using those values. So all these values are plotted. All these values are plotted on the diagram using our basic concept. So which basic concept is there? First of all, we start our diagram with a 0 value at point A. Then we apply our shear force at point A, that is nothing but 80. 80 is positive, that's why we plot it above the 0 reference line. This is our 80. Then we move forward up to the point C. At point C, we got the answer as a minus 20. As it is the minus 20, we have to move in the downward direction. But what we are going to do? We are going to subtract the value of UDL first. So what is the value of UDL? UDL is nothing but 10 into 2. What is the value of 10 into 2? That is 20. If you subtract it from the 80 kilonewton, you will get the answer as 60. Now this 60 is positive. That is why we have represented it above the reference line. And we got the answer as minus 20. So minus 20 is represented below the reference line over here. After that, we move forward, carry forward this position up to the D point. Why we have carry forwarded it? Because between the C and D, there is no UDL acting. If there is a UDL, we have to join the points using the inclined line. Now we are connecting the points with the horizontal line. Now, if you take the 60 kilonewton, then you will see that there is a minus 60 kilonewton acting on the point D. So due to minus, we have represented it in the downward direction like this. We carry forward this up to the next point B, because as there is no UDL acting on B in between, that is why we carry forwarded it up to the point B. Now at point B, the value is minus 60, and at last the total answer will comes out to be 0 to complete our shear force diagram. So this was our entire shear force diagram. Now what we are going to do, we are going to take the calculations of bending moment. What is the bending moment? Bending moment at point A and point B will always be equals to 0. So at point A and B, we will start our diagram with 0 values. After that, the remaining points will be the point C and D. So if you can see over here at point C, we are taking one section. In the left hand side, there are two forces acting on the left hand side. First one is the RB. RB equals to 80 kilonewton. 80 into 2 going in the clockwise direction. 80 into 2 clockwise. That is why we have taken it as a positive. But UDL always goes in a downward direction. So due to downward direction, it will cause anti-clockwise moment. Anti-clockwise moment, that is why it is taken as negative. Now the distance between the UDL and point C is exactly the half of the UDL length. So UDL length is 2 meter, and that is why this much half distance is 1 meter. So this is how we calculated the moment due to UDL. Taking the algebraic sum, you will get the answer as 140 kilonewton at point C. Now we have plotted the 140 kilonewton at point C like this over here. But you have to notice that the connection of point A and C is a parabolic curve. So this is our parabolic curve. Why we have used it? Because between the A and C there is a UDL acting on the beam. That is why we need to connect it using the parabolic curve. Last point is MD. MD is nothing but 60 into 2. Why is it so? Because we are taking D point and taking a reference section or imaginary sections over here. This imaginary section can be evaluated using the left hand side or right hand side. So on the right hand side there is only one force, so it will be easier for us to calculate using the right hand side. And this 60 kilonewton is going to give us a negative, or we can say that anti-clockwise moment. But according to our sign convention, on the right hand side anti-clockwise moment is positive. So 60 into total distance 2 will give us the answer of 120 kilonewton. 120 kilonewton into meter. So this is how our total answer of point D is represented. But if you notice, from between the C and D there is no UDL. So we have connected the diagram using the inclined line. Inclined line. And lastly, at the point D and B, we have also used one inclined line. So this is how the entire bending moment diagram is formed or drawn. Using which, using this method, you can solve any example which has the combination of the UDL and point load loading. In the upcoming lecture, we will see the combination of the UDL, point load and free moment also. Along with that, we are going to look at the examples of cantilever beam. So till then, thank you.